I have a gift.
A special gift.
I'm really good at video games.
Ever since I was a kid, I've been honing my gaming skills on my NES clone.
As years passed by, the games evolved, so did my gameplay.
You could say I'm the epitome of bro gaming.
Enemy at the center.
Son of
Or at least I thought so.
In case you didn't realize, I was the one getting slaughtered.
Okay, I might not be a good gamer anymore, but I'm a pretty darn good engineer.
Who do you think you are? Mark freaking Rober? First, let's understand the problem.
We suck at video games.
Okay, not that. First, let's understand what an aimbot is. It is essentially an external program or means that aims the character's weapon at the enemy while playing first-person or third-person video games. For example, let's say I'm playing a game where I encounter an enemy. If I'm not good at aiming and I'm aiming all over the place, the enemy will definitely go for the kill. We don't want that to happen. In order to gain an upper hand, I should be able to react faster than the enemy and optimally go for the headshot. To build a system that does this, first we need to capture what's on the game screen and do some pre-processing on the data. This data can then be fed into an algorithm, preferably an AI model, that identifies enemies in real time and spits out coordinates of enemy positions on the screen. Next, we need to move our mouse pointer or crosshair to these coordinates and shoot while fooling the anti-cheat engines in games.
Capturing what's on the game screen is easy as there are multiple libraries available. We have used Python's MSS library that captures multiple screenshots to record the screen. The aspect ratios of these screenshots are adjusted based on the monitor resolution and fed into a detection algorithm. We use YOLO V8, which is the new state-of-the-art object detection and instance segmentation algorithm. It has been shown to have high rate of accuracy on COCO and RoboFlow 100 datasets. The algorithm detects the object of interest and creates multiple bounding boxes around them. YOLO uses non-maximum suppression to eliminate bounding boxes with low detection confidence and retain the ones which accurately identify the object of interest. Let's say the detection confidence threshold is 0.5. That is, we want YOLO to be at least 50% sure that the object of interest lies within the bounding box. Now, the bounding boxes with confidence of less than 0.5 can be eliminated. Next, we select the bounding box with highest confidence and calculate the intersection over union with respect to remaining bounding boxes. For example, if we set the IOU threshold to 0.25, any bounding box with the IOU of higher than 0.25 is eliminated because they are all identifying the same object with lower confidence. We repeat the entire process until we segment all the objects without any duplicate bounding boxes. YOLO V8 uses optimizations such as anchor-free detection to predict the center of the object instead of randomly guessing the offsets of bounding boxes. This reduces the number of box predictions, speeding up the NMS.
Now that we have an object detection algorithm that returns the coordinates of the enemy position, we just have to figure out a way to get around anti-cheats. Most anti-cheats can detect non-human-like behavior, for example, moving the mouse in an exact straight line. To get around this, we can determine the motion between the initial point and the target using higher order curves for a nonlinear motion. Let's say the current position of the mouse is x1, y1 and the target position is x2, y2, and we want to use second order curves to determine the trajectory of the mouse pointer. For this, we can write two sets of equations with two known points, that is x1, y1 and x2, y2. But we have three unknowns, a, b and c. In this case, we can guess the value of one of these unknowns, say c, and solve the system of linear equations to determine a and b. We coded this up in Python and this is not the smoothest mouse pointer movement that I've ever seen. We can tweak some parameters to make it better, but just out of curiosity, We Googled around to see if someone smarter than us has already solved this problem, and indeed they have. There's a Python library called PyHM which mimics human movements and does this way better than our solution. So, like any good engineer, we decided not to reinvent the wheel and just use the available package. Now that we have all pieces of the puzzle, we put everything together and we're ready to face any challenge. What just happened?
Apparently, you can't use Win32 APIs in games because games use something like DirectX for handling mouse events or write their own raw mouse input library to intercept mouse events.
That does it. Time to pull out the big guns. We used serial communication to send out the coordinates from the AI model to the Arduino board, which acted as a human interface device, aka mouse, and moved the mouse pointer. Of course, there were some issues such as the Windows driver only supporting relative motion of the mouse pointer and the driver API only accepting a signed character in the range of -128 to 127, which we got around by moving the mouse in a piecewise linear motion.
Anyways, we digress. We only had to lose a couple of days of sleep and probably have some brain damage at this point. But it was all worth it. At this point, we were invincible.
We don't need a shield or a sword to face the battles of this world. We have something stronger and more sublime.
The power of our minds and our hearts, aka our Aimbot.